this time. So welcome everybody for the second session of today. So just as I've done so far, just showing you once again the flyer of the school. Again, all the presentations are on the YouTube channel, which we created for the circumstance. And today, for the second session, the moderator will be Andrew Millis from the Flatiron and Columbia University, and the speaker, Cristiane. And I will pass the baton to Andy, who will be the moderator for this session. So first of all, I will stop sharing my screen, and I am going to appoint Andy the host.
All right, thank you very much. So I hope I am audible.
You are.
Yes, great. Okay, so welcome everybody. Today it is our privilege to have Cristiane Morais-Smith present a seminar in this Les Houches school. The format for seminars is a little bit different from the format for lectures. So Cristiane will speak for approximately 75 minutes, and then there will be approximately 20 minutes for questions afterwards. So to keep things flowing, we would prefer that you hold your questions until the end of the presentation, at which time there will be plenty of time for questions and discussion. If something comes up, during the talk an urgent issue comes up of clarification, meaning that you would like information just to make sure that you understand what is being said, put your question in the chat, and I will either answer it myself, or if it's essential, interrupt Cristiane and have the question answered. Otherwise, put your questions in the chat and labeling them. And if you do that, label your question as urgent. Otherwise, put your questions in the chat window, and we will get to them at the end of the presentation. And for each question, I will ask the person who asked it to unmute themselves and explain their question, and then we will proceed from there. Okay, so those are the ground rules. Now, Cristiane Morais-Smith is currently a professor at the University of Utrecht and is known for her work basically linking interesting quantum physics to design of the environment in which these quantum systems live, both in terms of condensed matter systems and cold atom systems. In particular, the interplay, let's say, of topology, correlations, and material structure in a generalized sense. She was educated in Brazil, I believe at the University of Kempkes, did her PhD with Amir Caldeira, was a postdoc at the ITP, the Institute for Theoretical Physics in Zurich, and then after academic positions in Hamburg and Fribourg, was appointed full professor at the University of Utrecht about 15 years back. She has written a large number of outstanding papers in these and other areas, and her work has been recognized by the 2016 Dresselhaus Prize and the 2019 Emmy Noether Distinction of the European Physical Society. And today she's going to tell us about atom by atom construction of quantum states of matter. So Cristiane, please share your screen and take it away.
Thank you very much. Do you see my screen?
Yes.
Okay, very good. So let me start by acknowledging the organizers for the invitation, and especially Marc Gabert, who even sent me a tour, a virtual tour over the Mont Blanc that I was so much keen to do in reality, but I at least got a video. So let me start telling you about how we have been doing atom by atom design of novel quantum states of matter. Yes. Okay, so Feynman has left us a huge legacy in terms of path integrals, Feynman diagrams, etc. But one of the very important ones is the idea of quantum simulators. So about 6 years ago, he gave a talk where he pronounced this very famous sentence, "There is plenty of room at the bottom." And with this sentence, he was trying to instigate us to not only investigate matter, but to build matter in the way how we want it to perform. The idea was very revolutionary at the time. It might sound banal nowadays, but it took quite a while until the community started doing what he was suggesting. The field of quantum simulators started with cold atoms. So people started making lattices of light and putting atoms into them, and simulating, for instance, the Bose-Hubbard model. And this is more than 20 years ago. So this field has progressed already a lot. And since a few years, also in photonic systems, people started using waveguide arrays to simulate lattices and other quantum systems. But in these systems, you would have atoms or photons, not really electrons. And in a world which is mostly based on electronics, you wonder, why aren't we yet building quantum simulators with electrons? So that's precisely what I want to talk about today. And most of the talk, except for the last subject, I will be concerned with using surface states of metals like copper and patterning the lattice on top of this 2-electron gas that lives on the surface of this metal. Okay, so I will give you an outline of the talk. So in the very beginning, I will show you how to control geometry, and I will show you that we have built this Lieb lattice. Then I will tell you how to control orbital degrees of freedom. So this is one internal degree of freedom that we were able to control in the systems. Afterwards, I will tell you how to generate flat p-bands. So flat bands has attracted much attention recently, and here we will generate the ones in the p orbitals. Afterwards, I will show you how to control topology and what kind of the edges appear in this Kekule lattice in terms of topology. And still in terms of controlling topology, we will look at a higher order topological insulator in a Kagome lattice. And finally, I will come to the issue of controlling dimension. This is the longest part of the talk, where I will show how to build a fractal, a quantum fractal, in the STM setup, and afterwards using waveguide arrays to study dynamics. Okay, let me then start with the birth of this topic. Quantum corrals. Everything started in 1993 in the group of Don Eigler, when he built this first structure that I am showing you here. So this is a 2-dimensional electron gas that you are seeing here. And on top of it, he has been patterning atoms of iron. So these spikes that you see in yellow are the atom irons, the iron atoms, and he has putting them in the shape of a circle. And when he did this, the 2-dimensional electron gas that was here in between, he started getting interference patterns and forming waves. So the waves that you watch here are electron waves, and he called this a quantum corral. So this was a beautiful experiment. It's the first time that people confined by hand this 2-dag in a certain way by patterning. And this was then iron on copper 111 surface. But it took almost 20 years for us to go from this confined surface into the formation of a lattice. And this has been done by the pioneering work in the group of Hari Manoharan in Stanford. And now he was patterning carbon monoxide molecules on copper. So what did he do? You can see here this yellow figure. This is the 2D electron gas, so a gas of electrons in 2 dimensions, free electrons. And the brown dots are carbon monoxide molecules. So these are adsorbates on top of the surface. They go randomly everywhere. And now what he does is that with the tip of his STM, he picks them up one by one and puts them in well-defined positions. In the case here, he is putting them to form a triangular lattice. And these barriers are like little mountains, like the Mont Blanc that we are not seeing at the moment. So when you arrange these barriers, forming a triangular lattice, the electrons go around and form a honeycomb lattice. So he called this setup a molecular graphene system. And as you can see here, this is the local density of states. If I don't tell you that this bar here has 2 nanometers, you would not be able to distinguish this from graphene. So it really mimics graphene, but on a scale that is 10 times larger. And when he measures the GIGV, so the variation of the current as a function of the voltage here, you will see also this shape, this V-like shape, which is the shape that you see from the Dirac cone in the dispersion of graphene. So this has been a really very important experiment because it's the first time that someone has built a lattice using this patterning, and this is a lattice built in the nanoscale. So the separation between 2 COs is 1.1 nanometer. So it's really a fantastic experiment. But there were some buts there. So the first but is that, okay, if you want to build a triangular lattice, you know the anti-lattice, because what you build is the anti-lattice, which is triangular to get a honeycomb. And in addition, this triangular lattice, it fits very well the copper substrate, which is also triangular. And you can only put the COs on top of copper. So the question then that we had is, if we can only use this to pattern triangular lattices, we are not going very far. Can we pattern any lattice with any generic geometry? For instance, a square lattice. So that was the first question that we had in 2017 when we entered this field. And the first idea was then to try to control the geometry. For this work, I want to call the attention of Marie-Louise Lott. She was the PhD student doing the experiments, and Peter, he was doing the tight binding calculations. And the experiments were performed in the group of Ingmar Svart and Daniel van Makkelberg. Ingmar is the specialist in STM. Okay, so what did we decide to build? We decided to build a Lieb lattice because the Lieb lattice is more interesting than just a plain vanilla square lattice. So what is the Lieb lattice? It's a square lattice which has these sites, also the red sites in the middle of the bonds. So there is a missing blue one here to be a simple square lattice. The Lieb lattice is very interesting for many reasons. First of all, this is the true lattice of perovskites, like high-TC cuprates. You would have copper sitting at the blue sides and oxygen at the red sides. Second, it is a lattice that has 3 sites per unit cell. So in terms of some pseudo-spin description, it goes beyond graphene that has just A and B sublattices. Pseudo-spin 1/2. This one is pseudo-spin 1. Third, it has a very interesting energy dispersion. So energy versus K, you would see 3 bands and you would get a Dirac cone, so the upper and the lower band, and a flat band in the middle. So it has, it combines flat bands with Dirac cones, which is also very interesting. And the other thing why I find it so interesting is because we usually treat lattices that have sites that all have the same connectivity. But here, the blue sides have 4 neighbors, whereas the red sides have only 2 neighbors. So the sites have different connectivity. What is very nice if we are investigating this type of lattice using a scanning tunneling microscope is that when you try to probe the local density of states, referring to this band structure, for the Dirac cone, you would see this V-shaped structure, as Manohara has already seen for graphene, but the flat band would have a huge peak because it has a very large density of states. So it's a nice system to probe. But the question is how to pattern the anti-lattice to get this type of lattice, the Lieb lattice. So this is what we have been doing. You see what we do. So first of all, you put all the COs around here to make a kind of a box to confine your structure. And then we have been putting 5 COs because now the electrons will go into atomic sites, which are defined by the space between the COs. So we would imagine that they would sit at the blue and the red sites that I am representing here, and they would form a Lieb lattice. So then what you do is you position after you have built, and you take a topographic image with STM to see that you have built what you wanted, that all these COs are in the precise position, not displaced by one atomic site. Wrong. Now you sit on top of the, let's say, the red spot, and you measure the GIGV, and you renormalized with the GIGV that you would have if you would not put the COs on top of copper. And you would see the features which are here. So you see this big feature as I would expect for the Lieb lattice. And if I sit on the blue side, I would see this V-shaped structure that you are seeing here. So it looks very nice. It seems that we are indeed getting the features we expect for the Lieb lattice. We can then compare this with the results we would get out of calculations. And I will show you in the next slide, we are doing 2 types of calculations, what's called a muffin tin and then a tight binding. And what I'm showing here is the result of the tight binding calculations, which captures all the main features. So let me show you now the calculations that we are doing to try to understand this system. It's basically very simple, and we are doing 2 types of calculations. It's all non-interacting. You would in principle think, non-interacting physics, that's not very interesting. I hope that you will be surprised by how much one can do with a system of non-interacting electrons. So we have the electron gas and we know the effective mass. And now the muffin tin model is as simple as baking muffin. You put here a tin that confines your entire structure, and now you invert the muffin tin here. So the CO is going to be represented by these barriers, by these mountains, and the electrons are just flowing in between. Okay, so they are repelled by these barriers. We know the diameter of the barriers and we know the potential. So we can simply solve a particle in a box Schrödinger equation for the specific shape of the potential that is given by these 5 COs in the center, how I have been showing you before. And with this, you can get your energy structure. And now the question is this finite size system representing the same physics that I would get out of an infinite system described by a tight binding picture? So what you do now, you try to calculate for a tight binding approach the energy levels in a way that you match with the energy of the muffin tin. And now you will get the description that I have shown you before after you define parameters like hopping for nearest neighbor and next nearest neighbors. From there, you can see whether indeed this small finite size system is showing the same features as the infinite system. It all works extremely well. Okay, so we have done that and we have shown, okay, we can generalize and build square lattices. And then you say, okay, what next? Well, I would like to control some degrees of freedom. Controlling spin is not very easy in this lattice, but there is something that we can control and it's very easy to control, which is the orbital degree of freedom. And this is not very easy in other systems. So every kind of system we build will have its own advantages. And that's what we have been last year doing. And again, Marlouis Loft was the main person behind the experiments, and Sander Kempkes was the main person behind the calculations. Sander is a PhD student in my group. The experiments were performed supervised by Mar Zwart in the group of Alex Kajetodians in Nijmegen. We used his setup because it was free at the moment. Okay, so what did we do here? So I have shown you before that when we were measuring this structure, we were getting the electrons sitting at the white spots, which are here represented by green. And these measurements were performed at voltages of 50 millielectron volts, 50 millivolts. But now, if we go to 550 millivolts, to much higher energies, what we see is that instead of seeing a maximum, which is usually light, where the green spots are, now we start seeing dark spots, which means it's a node. This tells us, or suggests at least, that we are probing px and py orbitals when we come to these higher energies. And then, so this is the size of the real setup. Now I will show you just a little spot, which is just one unit cell. So indeed, if you do the calculations for the energy as a function of the main points, main symmetry points in the Brillouin zone, you will see that up to about 300 MeV here, we would be probing the S bands, but at 500 MeV we are here, we are probing px, py orbitals. So you can now look here, this is a zoom in the figure that we had before. On the left you see the experiments, on the right you see the muffin tin, the theory. And indeed we can see that the high density of states is where we expect, where the lobes of the px and the lobes of the py are overlapping. The particles are sitting mostly there. Okay, so we have been designing a px-py orbital in the Lieb lattice. But can I decide which orbital goes to which site precisely under demand? Can I control? I want only this orbital here and here and here and I want. That was the next step that we decided to do. So for this, we changed the design, and instead of having the 5 that we had in the center here before, now we put 12 COs, 4, 4, and 4. And as you can see, now it's not possible any longer to have a px orbital here, and it's not possible to have a py orbital here. So with the design, I can precisely engineer my lattice to have only px, only py, and py and px at the corner. So again, these are the experiments, and this is the theory. And you can see the yellow parts are the high density of states. They are precisely in agreement with what we thought that they should be. So we can engineer orbitals in the lattice in a nanoscale precision. But the px and py energies are still degenerate. And now what we would like to do is what Zeeman has done for the spin of the electrons. Usually the spin of the electrons are degenerate. And what Zeeman found out is that if he puts the setup in a magnetic field, you separate the energy levels of the spin up and the spin down. And here we would like to separate the energy levels of the px and py orbitals. So how to do that? The answer is very simple. The way to separate, here we don't need any magnetic field. The way to separate these energies and to lift this degeneracy is to break the C4V symmetry of your lattice. So now we build another lattice, but now it is a rectangle. You see, it's the pink is much larger than the blue. And in this rectangular lattice now, you can see, so experiments are on the left, theory is on the right, and on the top, we have the experiments done at plus 50 MeV and the calculations also. And you see that now you only see yellows along the X direction. And when I come to minus 50 MeV, I only see the yellows along the Y direction. So I have been lifting the degeneracy between px and py orbitals, and I found a way to completely care for that. Let me tell you one thing. If you are looking at this very carefully, you will see there is some yellow here in the middle where I'm putting my 12 COs. This is just a contamination. At the time, we didn't know that we could still put one more CO here, and we could have done it, and this doesn't belong to the features that we are describing, okay? This could be improved in a post-experiment regard, and simply not have it there. The lattice that we are looking at is what is behind. Okay, very good. So we have until now controlled the orbital degrees of freedom, and in the Lieb lattice we understood how to precisely engineer where the px and the p orbitals go. Can we do more? Can we engineer, for instance, can we separate s and p? Can we do more things with these orbitals? So that's the work I'm going to tell you now, and this work is on ArXiv. And I want to underline two main persons in this work, the two PhD students, Thomas, who is the experimentalist behind the measurements in this part, and Jette van den Broek, who is a theoretician in my group, and she has been doing the calculations. And I want to show you the photo of Daniel here because he has been leading this work. Okay, so if we go back to the original lattice by Mannerheim, so you remember Mannerheim was patterning the black ones here, which are the COs in a triangular array, to form the lattice, which is given by the gray, which was the honeycomb lattice, right? If you look at the energy level here again, in terms of the high symmetry points of the Brillouin zone, you would see here there is your Dirac cone. But the higher bands, you see, they are dispersive. And what we realized is that, these are calculations by Jette, if instead of putting one single CO, you put a rosette with 6 COs, what happens is that now the P band starts to be flattened up, and you start to see here also a Dirac cone, a p-Dirac cone. But if instead of one layer of rosettes, you put 2, look at that, what a beautiful thing. You are now able to separate the S bands from the P bands. And you then are able to see this flat band with this very huge density of states here, with a huge peak, which is signaling this P band. So this would be a way in these artificial systems to access physics that we cannot do in real graphene. In real graphene, the S and PX and PY bands, they are hybridizing, they form sp2 bonds. This is what gives rigidity to graphene. So there is no way to separate S from PX and PY, but here we can. And we can even open a gap that is so nice in the system and really have only the p orbitals in this honeycomb structure. So we then went to perform the measurements after Jette had done all these calculations about where and how you should put each of the COs to get the effects that you want. And indeed, you can see here, the measurements are on top. So if you sit on the green sites where you would expect this the honeycomb to be, especially for the S-like, you see here this S-like orbital. You see the P band in the violet, which is coming mostly from this part of the contribution, which is this huge density of states. And here you see also the P Dirac cone. So there is an S Dirac cone, a P flat band, very flat, very huge peak, and a P Dirac cone. And this is what you would see in the images of the local density of states experiments and theory underneath, if you would be looking at the S Dirac cone. And this is what you would see if you would look, so up is experiments, down is theory. If you would be looking here at the flat band, and here at the Dirac cone in the P band. Okay. Very nice. So we can again control further the S and P orbitals in the honeycomb structure. Good, so we have been controlling geometry, orbitals, flat p bands, and I would ask you, yeah, now what next? What interesting should we try to do with the systems? And the answer would be topology. Topological insulators are such an interesting system. Can we produce topological states of matter, understand them better, and control them in some way? So the thing that I will first tell you is about how to generate zero modes and how to construct a higher order topological insulator with electrons. It was the first realization of a Houches with an electron system. It was published also last year. And again, the main players in the theory are Sander Kempkes and Jette van den Broek, my two students in theoretical physics, and experiments were done by Marloes Lot. She was the main person behind them with the help of some colleagues. Okay, so what are we going to build? Before I tell you that, let me give you a very short introduction. I am sure you know that, but just to set up the conversation. So topological insulators. In the last century, we have been classifying metals, insulators, and semiconductors. And you know that insulators have a gap in their energy spectrum, and metals, they are conducting, right? And suddenly this century, we learned about this new type of matter, topological insulators, which are both insulating and metals at the same time. They are insulating at the bulk, and they have metallic edge modes, which are here at the boundaries of the system. When I look in terms of energy versus momentum, the bulk bands have a gap. It's the white part between the light gray things here. But now, because of these metallic edge modes, there are states in this gap. If it is a topological insulator that's produced by spin-orbit coupling, I will have two crossing states here, crossing at the middle at the zero energy. And this is a signature of the spin up and the spin down counter propagating edge modes. But last year we got a new notion, which was very interesting, which is the so-called Houches, higher order topological insulators. And now, if I would have a bulk in 2 dimensions, for instance, as I was drawing before, instead of having my topological edge modes in 1 dimension, which is 1 dimension lower than the bulk, now my edge states, my topological states are at least 2 dimensions lower than the bulk. So if my bulk is in 2 dimensions, my edge modes would be corner modes, 0 dimensional corner modes. And now in my energy versus momentum spectrum, they would be just a 0 mode sitting there at the 0 energy. These are the so-called higher order TIs. If I would be in 3D, I would have hinges around, 1D hinges around the material. Okay, so that's what we would like to build with electrons, because people have built them before using photonics, for instance. Okay, there was a proposal, very nice, by Ezawa in 2018. And the proposal was to do and to look at a breathing Kagome lattice. So what means breathing? This is a lattice. So first of all, the Kagome lattice is the lattice that you see here in the middle. It has looking down triangles and looking up triangles. So there are hexagons and these triangles looking down and up. It's a very interesting lattice, and Miles loves them, looking for spins in this lattice. It leads to frustration. It's a very interesting lattice. And now you build this lattice, but with bonds that can be strong or weak, like in the Sushri-Fihiger model for polyacetylene, where you have 2 types of hoppings, strong and weak. You do the same here. And now you see that if you would have no weak bonds here, such that your last corner of your triangle is isolated, this would have some 0 modes, your isolated modes at the corner. And now, if you would have them strongly connected, they would be forming these trimers, there are no zero modes anymore. So the first one would be trivial, topological, and this one with the trimers would be trivial. But you could have some TA that is smaller than TB, and the zero modes should still remain in this regime. So that was the prediction that was made by Professor Ezawa. And we thought, okay, let's try to engineer such a lattice. So you see here again, this Kagome lattice. And now I am painting all the sites in the bulk in green, the corners in blue, and the edges in yellow, okay? And every time we will sit in each of these sites, many times you do many experiments to take average, but then we present you just one curve, which is the averaged curve. And we would like to now build this setup such that sometimes this last triangle here, the hopping between the sites in the uppermost triangle is weak. This is the TA. And sometimes when this hopping is strong. Usually in lattices, the weak or the strong hopping are controlled by the distance between the sites. But we control the hopping by the amount of barriers that we put between them. So you can see here, this is the design for the non-trivial configuration. These black spots with the green circles around them are the COs. And you can see here, I am putting 4 COs in the middle. So to hop between here and here, it's very difficult. So here, there is a very narrow a constriction for the electrons to hop between the blue and the yellow sides. So this will be a weak hopping, this will be a weak hopping, and this will be a weak hopping. So this is a non-trivial lattice. Whereas here, there is just one CO. So this is a strong hopping, okay? This will characterize a trivial lattice. And it alternates weak, strong, and so on. So you see now that when you sit at the bulk, at the edge, or at the corner for this lattice, for the trivial lattice, you will always measure the same thing. The upper part are the measurements, they go on top of each other. And this is the calculation from the theory, tight binding. But here, in the non-trivial one, you will see there is a peak in the green, another peak in the green. Here, a peak in the yellow. There is some overlap between the yellow peaks, but then the blue has a maximum over the minimum of the green and the yellow peaks. These peaks overlap because we have scattering with the bulk, so they are not perfect peaks. They have a certain width. So, but now what we can do is, but this is an indication that we have a topological corner phase. Now we can sit at well-defined positions, at well-defined energies, sorry. So you can sit, for instance, here at the maximum of the green, or here at the maximum of the yellow, or here at the maximum of the blue. And now you scan your entire sample and you take the maps of the local density of states. So these are the experiments in the vertical line for the non-trivial. These on the right are the experiments for the trivial. Let's start with the trivial. If I am at minus 110 MeV, at 5 MeV, or at 50 MeV, I see the same pattern everywhere, in the bulk, at the edge, or at the corner. But in the non-trivial one, first at minus 110, I see the red. The red means high intensity. In the bulk, then it goes to the edges, and then it goes to the corner at 50 MeV. You see the red are at the corner. And here is the theory, and you can see how you go from the bulk to the edge to the corner modes. So we could generate corner modes in our setup. Now, the question is, how resilient are they to disorder? So if now I take away a part of this lattice, you see here, there are parts missing. And when I come to 50 MeV, do I still see my zero modes? Look how nice, they are there. Just the one that I cut down is no longer there, but the other two, they were unaffected. If now I add another protrusion in E, I am putting another part into my lattice, which breaking some of the symmetries too. What happens? Look at H, 0 modes, they are still there, unperturbed. And now if I add a protrusion that has a 60 degrees angle here, look at that. At the last bottom picture, I am adding one more 0 mode because now this has 60 degrees and these are the ones that can host the 0 modes. So I can destroy 0 modes or create them at will by engineering my lattice. That's very nice. You know, the people are trying to create 0 modes as qubits for quantum computer. The ones that they are creating, these are non-abelian 0 modes. They create in a superconductor using the Kitaev chain. Those are abelian 0 modes. They are not, they don't have the properties of those ones. But people have been also trying to understand, can I use abelian 0 modes like the ones I get in the Sushriff-Higger model to construct quantum computers and to perform certain computer operations, and this has been shown to be possible. Okay, very good. So after the geometry, the orbitals, and the Houches, what next concerning the topology? So we wanted to investigate another very interesting feature, because by now, when we look at topological states of matter, we know about the ones that were 30 years ago quantum Hall effect systems that appear in the presence of a magnetic field. We also know the other ones like the quantum spin Hall effect that appear when you have a spin-orbit coupling. That's very strong. But now, more recently, people talked about these crystalline topological insulators. And these are now topological states that emerge from the crystalline lattice symmetries. And the question is, how similar or different are they to the others? For instance, for the others, the edge of my system, I create a system, and the way how I terminate it is irrelevant for getting a topological state or not. If I have a strong spin-orbit coupling, I can take the structure that you want and terminate the way you want. You will see these edge modes. The same for a high magnetic field for the quantum Hall effect. But how is it for these topological crystalline states? This is going to be different, and I will show you in a minute what happens here. Let me just call the attention that this work, it has just appeared in PRL, and the experiments were done by Sarsha Frene, and the theory was done by E.T. van den Broek. Okay, so what are we going to build here? Here we are now going to build the so-called Kekule lattices. What is a Kekule lattice? Again, it is a kind of a graphene lattice, but now I am going to have the hopping T0 inside the hexagon and T1 connecting to the next hexagons, okay? And we are going to investigate 2 types of lattices, the ones that have a very strong T0 and a weak T1, and the ones that have a weak T0 and a strong T1. And in addition to that, we are going to look at different kinds of edges. The ones that are called molecular zigzag, the ones that are called partially beard, you see the beard coming out, here, and the so-called armchair, because this looks like the chair of the arms of a chair. This is the least interesting one. I'm not going to show you. I'm going to show you results for the other 2. But why are we specifically taking this type of edges? Why not just a normal zigzag, as people looked at in graphene nanoribbons, for instance? Because the usual zigzag edge, you terminate with only one sublattice. Graphene has 2 types of sublattices, A and B, because they see different neighbors in the honeycomb lattice. And if you terminate with only one of the sublattices, you immediately get 0 modes. So that's not so interesting. We have to find terminations where you have both A and B sublattices terminating in equal numbers to do not get any spurious effect of favoring one of them. okay? And in these two types of lattices that we are going to observe, this is the case. Okay, so there had been a prediction by the group of Professor Hu, and he has been looking at these lattices theoretically and claiming that depending on how I terminate these lattices, depending first of all, if T1 is larger than T0 or smaller than T0, for a certain termination, one of the lattices would be topological and the other not, okay? And this would be the opposite when I would change the termination, if I would go from the molecular zigzag into the bearded, partially bearded edge. So that's then what we went on to design and to build. I want to call your attention to the theoretical work here is really finding the way how to design these lattices to be able to observe these effects. And this is really it requires many calculations, very careful calculations, until you finally find out, okay, in this configuration, I have a gap that's large enough that can overcome all the problems from the experiments. I am not introducing anything artificial in the calculation. For instance, let me show you just to get a feeling for it, how it goes. You see here, in this lattice, T1 is going to be smaller than T0. So we are going to have a very strong hopping. This red bond is strong because there is only one in the center, CO, and the barriers are turned like this. You see, there is nothing close to the bond here. So in this case, my T0 is large. But if we invert, and now we put 1 pointing at, and instead of only 1 in the center, you put 6. Now, these barriers here make that this hopping T0 is going to be weak. And then T1 is going to be strong. But here is the opposite. Here, T1 is going to be weak because there are these two COs pointing at each other. And here not, there are these voids pointing at each other to make this T1 strong. And then when you have to decide how to terminate your sample, you have to close your box somehow to avoid leakage to the outside world. But when you put more COs here, those I'm talking about the ones in red, you might change the on-site potentials, and you don't want. You want your external part to have the same on-site potential as the bulk. So then Yete has been doing all these calculations, moving these COs one by one, each atomic position, to really find the ideal setup to build that. These 4 lattices that we have building, so with the 2 types of T0 and T1 with the different terminations, are really state of the art, which was a huge number of COs, more than 400 per lattice that Sarsha had to manipulate. Okay, so you build these structures, very nice. And now you are going to position yourself at certain sites. These are the structures seen with the topographic image for the partially bearded and the molecular. Now you sit at the black spot, at the blue, the violet, and the red, and you take the spectrum. If you sit in the orange, green, and yellow, and blue, of the right-hand side, you see on top the experiments. This is a trivial configuration. The theory confirms they would be, all sites would be exactly the same on top of each other. On the other hand, on the left-hand side, you can see that the black and the blue have a dip, but the violet and the red have a maximum. You see the same in the calculations. Now you sit at this maximum, and you take the local density of states in the entire sample, and you see the experiments on top and the theory at the bottom, and indeed you see the sample that had the molecular zigzag termination. You see the bulk is precisely the same. You see that the hexagon here is very thick, and the connections to the next hexagon is very thin. It's precisely the same, it's the same bulk. But the termination changes. And for this termination on the right, your sample is trivial. For your termination on the left, your sample is topological. And you can see the edge mode running here by these white patterns in the high density of states. And you would ask, but how can this be? The reason is that these topological crystalline insulators, what happens is that the choice of the unit cell will determine whether they are topological or not, and the termination defines the choice of the unit cell. So the termination definitely decides whether they are going to be topological or not, together with the bulk. The bulk also is important, the shape and the termination, okay? So now we go to the other lattice. Now you see that now these hexagons are thin and the link between two hexagons is thick. And now look at what happened. If I sit at the violet, red, or black spots, in this lattice, everything is trivial. When I come to the molecular zigzag, I see that the black and the green are having some minimum, but the yellow and the blue have this maxima. And when I again sit at these energies, I will see that now it inverted. The partially bearded has no topological state and the other one does have. And the same can be seen in the theory in agreement with the experiments. So we got to understand that the shape of the boundaries matter very much when we are studying these topological states in crystalline topological insulators. Okay, very good. So that was, I am doing well with my time. That was, I wanted to tell you until now. Now I will start with the last part because we have been looking at geometry, topology, orbital degrees of freedom. The next thing we want to ask is, how do electrons behave in fractional dimensions? And you will tell me what the frac. We would like to control the dimensionality. And this is a beautiful point for us to go beyond what exists in nature and to control that, to create a quantum fractal. Again, the experiments were performed by Marlou and the theory was done by Sander Kempkes. And the results were published the last year. And here, if you want to read more about that, there is also an article in Physics Today. They talked about that. And a beautiful video about quantum fractals made by Seeker on YouTube. Okay, fractals, what is that? Maybe you never heard about that. So fractals are these beautiful structures that most of the time have the property of self-similarity. You keep zooming in on a fractal and you keep seeing the same structure. Maybe you have seen the Mandelbrot set or the Koch curve, which is the shape of snow, or maybe you have seen what's called a Sierpinski carpet. This is a square in which you divide into 9 parts and you cut the central one. And then each of them you divide into 9 parts and you cut the central one. Each of them you divide into 9 and you cut the central one. That's the Sierpinski carpet. Again, you can observe the self-similarity. And the other nice thing that a fractal has is the so-called fractal dimension, which is no integer. This is also called the Hausdorff dimension. So we are going to talk about the so-called Sierpinski fractal, which has a dimension 1.58. Let me explain to you how this comes about. The dimensionality, the Hausdorff dimension, is given by the log of the number divided by the log of the scaling. What is the scaling and what is the number? So let's look. Take a straight line down here in red. And now you scale it by a factor 2. This is the 2 that is here on the left-hand side. And you got the black one. Now you ask yourself, how many of the original ones can I put on top of this one? 1, 2. You get the number on the right, 2. It means I am in 1 dimension. The exponent gives me the dimension. Go to the top. I have a red square. Scale the red square by 2. On the x and on the y-axis, you get the blue square. How many of the red squares I can put inside? 1, 2, 3, 4. You get the number 4. The exponent is 2. You are in 2 dimensions. okay? Now take this triangle and paint it completely in red, and paint this one completely in dark blue. Now you take the red triangle and you scale it by 2 here and by 2 here. And now you count how many of the fully red triangles you can put inside. 1, 2, 3, and 4 to cover the entire surface. I would be in 2 dimensions. But the Sierpinski triangle is a triangle in which I took away an inverted triangle in the center. I remained with 3. I took away another inverted triangle, and so on. So in the Sierpinski, there is nothing here in the middle. So the number of Sierpinski triangles that I am getting when I scaled by 2 is only 3. So log 3 divided by log 2 is giving me the dimensionality 158. That's how fractals, the fractal Hausdorff dimension emerges, okay? So fractals are structures that have voids. The concept of fractal is very closely related to humankind in nature. If I look at a Romanesco broccoli, I see a fractal. The trees, when I go for a walk in winter and I look at the structure of the branches, is fractal. The roots I usually don't see, but they are also fractal. The leaves, they are fractal. But also our body is fractal, our lungs are fractal, our circulatory system is fractal, our neurons are fractal. And even there is fractal dynamics in our body. Our heartbeat is fractal. And it's extremely important to be fractal, because if it becomes ordered, completely ordered, or if it becomes completely chaotic, we are ill. So fractals are everywhere around us and inside ourselves. They are extremely interesting in technology, because for instance, if I build an antenna out of a fractal, because I have short and long length scales, I can simultaneously send and receive large and small frequencies. They are very nice to build solar cells, because if you increase the complexity, you can't read it here, but this growing blue here on the right panel means that I'm increasing the complexity of the fractal that I'm patterning on the solar cells, and then I can store more energy. They are also very beautiful, and for that, they have been used in art since the century 11th after Christ. This is, for instance, a Sierpinski fractal in a church in Rome from the 11th century. You have been probably seeing many fractals if you go to some ADS-CFT talks. They love to take this picture by Escher, which is very nice, or a Pollock painting. It's one of the most expensive paintings in the world. And believe it or not, at some point, someone has found a Pollock painting and they were not sure whether it's a true Pollock or not. It could be a fake. And then there was a physicist looking at it and analyzing the fractal dimension of this painting, because it turns out that the fractal dimension in the work of Pollock has been increasing with the years. And by analyzing that, they could conclude that it was not a true Pollock. And afterwards, they confirmed also by other techniques. So fractals are everywhere in the world around us. Let me tell you some very funny thing about fractals. Our big friend was telling us that God does not play dice with the universe. But I keep thinking, is this really true? Maybe it does. So let me show you a game which is on YouTube. If you look for Quantum Chaos game, you would get it immediately. It's a very nice game. So let me show you. We are going to build a triangle and choose a random point inside it. Okay? So now we are going to play dice. I will call the corners of my triangle 1, 2, and 3, but because I don't have dice with only 3 sides, I have dice with a 6. I will continue and say this is also 4, 5, and 6. So if I roll my dice and I get 1 or 4, I come to this triangle, to this corner. I will connect my randomly picked point to the corner that I get by playing dice. And then I will choose the midpoint, okay? Then I play dice again. And if I get 1 or 5, I come here, 3 or 6, I come here. So let me show you how one plays dice and one starts forming this picture. Middle point, this is my new point. Roll the dice, got this vertex again, middle point. Middle point. Every time I connect a vertex and I choose the middle point. And I do it many times. And after you let your computer run, guess what? We get this beautiful Sierpinski triangle. So if our body and nature is fully fractal, and you can generate fractals out of a completely chaotic game, why not? How can we be sure that God's not playing dice with the universe? Okay, so these are fractals in the classical world. In the quantum world, we also have a few of them. I have shown you one that I like so much. It's from a previous paper of my student, Walter Böcheling, because he has been caring to put beautiful colors into it. This is the so-called Hofstadter butterfly. Energy levels as a function of flux per plaquette in any lattice for a perpendicular magnetic field. And what you get is that you get gaps which carry a quantum number characterized by the Chern number here, which tells you the number of edge modes you would have in the topological phase. These are these circulating currents that are carrying one quantum of conductance that characterizes topology.
Right, so excuse me,
this is,
just say we have about 14 minutes for the main part of your talk.
We have 1 hour, right?
1 hour has passed, so there's another slightly more than 1 hour, so there's 14 minutes left.
Yes, very good. Thank you very much.
Thank you.
This is perfect. Thank you, Angie. Very good. Okay, so this is then the Hofstadter butterfly. And the Hofstadter butterfly is one fractal that we encounter. It's a very beautiful fractal that we encounter in quantum mechanics. If you look at Anderson localization phenomenon, you get multifractality in your wave functions. This is now multifractality in the Hilbert space, or also in quantum turbulence. But these are fractals in Hilbert space, in a different kind of space, either energy space or Hilbert space. Okay, not fractals in the real space. And what we are going to build are these fractals in real space. So we decided to go for the Sierpinski lattice, also because the underlying copper lattice is triangular. This is a nice and easy thing to do. We are going to build here the first generation, the second generation, and the third generation of the Sierpinski gasket. It's called a gasket, is the triangle. You see on the right-hand side how we are positioning the COs with the hope that this would give us the first generation, the second, and the third generation Sierpinski. And we are going to describe again the systems in the continuum with a muffin tin and in the discrete infinite lattice by a tight binding description. So if you look here, you would expect that your sites would be characterized by the edges of the triangle in the center of the filled ones. That's why I get here this structure, like the red is at the edge of this triangle, the blue is in the center, which is filled by blue, and then the greens are here at the edges of this, where the voids start. We are painting these sites in different colors because of the number of neighbors. Red has 1 neighbor, blue has 3, green has 2, so they have different connectivities. And when we are doing the tight binding, you might be wondering, this is not a regular structure. This is not a lattice that's repeating herself. How can you do then the tight binding? So actually, people have been studying theoretically these fractals during the 80s quite a lot. There is a beautiful construction made by Kagome, for instance, where you can take this structure, map a mirror image of it on the upper side, and then you connect the red ones by periodic boundary conditions, and you can treat this iteratively as if it would be a lattice. You can also define quasi-Brillouin zones for fractals. So there are ways to find this structure to repeat itself. Okay, so these are the parameters for our tight binding models, and these are the experimental setups. And now we are going to come and sit on the red, the blue, and the green spots and take the GIGVs, normalized by the ones without COs, and you will see these features. Then we will do the calculations, and we will get that from the tight binding spectra. It looks good. And now we are going to identify 3 energies that look interesting. The ones here at minus 300 MeV, when the 3 colors, the 3 sites have the same intensity. The minus 200 MeV, when the red is very low and the green and the blue are high. And the minus 100 MeV, when the blue is low and the other 2 are high. And now we will sit at each of these energies and go with the STM over the entire sample to see the local density of states, which is modulus of the wave function square, okay? So you can see here on top the experiments, and at the bottom the theory. The vertical here, the first one is minus 300 MeV, minus 200, and minus 100. You can see for the bonding configuration, we had a beautiful Sierpinski triangle. At minus 200, you start partitioning the structure because the red was very weak, the blue was weak, right? Yeah, the red was very weak. And now here, when the blue is weak, you have the anti-bonding configuration. This would be an insulating structure because when the blue is weak, the blue is the one that has 3 connecting sites. You kill the connectivity of your triangle. Whereas here you didn't kill it completely, it's critical. Those are just the boundary ones, the red ones. Okay, the theory and the experiments agree very well with each other. And here you can see a 3D plot of the same thing for the bonding and anti-bonding configurations. But now the most important question. Do the electrons know that they are living in fractional dimensions? I am measuring the modulus of psi square. This is the wave function connected to the electron. Does it know that it's living in a fractal? And to verify that, that was the main question we were interested in, you use what is called Minkowski-Bulligand method, or box counting. And here I am taking the Sierpinski triangle for minus 300 milli-electron volts, and I'm projecting those peaks that you have seen, that the most white are the highest peaks and the grayish are lower peaks. So how does this method work? Looks very rough, but it's actually very good. It tells you, choose a box, can be a square or a circle, of a size reasonable compared to the surface that you want to cover. So if I want to cover all these white parts, I will not take a circle of this size because I will be taking black spots in between, okay? So let's say something like the pink circle. Now you cover all the white parts with this pink circle, and then you count how many you get. And then you plot the log of the number versus the log of the inverse radius, and you get a point, the pink point that is here, okay? Now you change the size of your circle, you make it slightly smaller, you cover everything again, and you count again, you get another point. Do again. You keep reducing the size of your circle and you keep increasing the size of your circle. And every time you cover as well as you can and you count and you get a point. The slope of this curve gives you the dimensionality of your object. And when we do that for this local density of states for the minus 300 MeV, we are getting 1.59, which is pretty good compared to the 1.58, which is the mathematical fractal dimension that I would get for an infinite fractal. So you can do that not only for minus 300 MeV, but for the entire set of energies. And you can also put error bars, and the error bars appear because I tell you that I'm covering in pink everything what's white. But what about this point? Is it gray? Is it black or white? Some of them are gray. So it's very difficult to decide what's white. And this is a kind of an ad hoc part in our theory. You say, okay, let's take 75%, but you could take 50% or you could take 90%. And if you take different numbers, you would get these error bars around the 75%. But what is interesting is that whatever you take, you are around 1.6. And if you do the same procedure for the honeycomb lattice of Manoharan, you are around 2. So it's definitely not 2, what we are observing. So the electronic wave function is in the fractal. And that's why we say we have built the first quantum fractal in space. Okay, funny is that this also works for the first generation. You see here in blue, green, and red, you are seeing for the different generations that this big one knows that it's a fractal, it's the green one, it's fine. But that the first generation for the tiny one already knows, that was very unexpected. Very good. So now I will go on. Until now, everything I told you was for building lattices with the STM with certain properties, but these are all static techniques. Now I would like to understand how is transport in a fractal network. For this, I need to go to a different technique, and we are going now to use photonics. And this is a work done in collaboration with the group of Professor Shanmin Jin in China. And let me show him in his lab. And I want to show you a picture of Xiaoyun Zhu, who is the person who did all the experiments and the first author behind this work. So here we are going to look at the quantum dynamics in fractals. And I could pose this question like the quantum ant in the labyrinth. So in the 80s, many people have been looking at a problem that was called the ant in the labyrinth. How should an ant behavior in a labyrinth, and how is the random process that it would undergo? And they have been looking at the classical random walk and studying how it would be, for instance, the exponents in mean square displacement to try to characterize this problem. And now we want to get a quantum ant in a labyrinth because this is a quantum problem. Okay, so as I have told you, the atomic manipulation setup that we have been constructing, or there was a beautiful one constructed before us by taking assembling of molecules in nature chemistry, or there is also one done in optics with some photorefractive material. All these types of Sierpinski triangles, they are not prone to the detection of dynamical properties. And for this, we are going to use this femtosecond laser direct writing techniques to pattern these fractals, okay? And you can do them in large scale, well-defined structures. And let me show you how they come. This has been done already to look at two-dimensional quantum walk. It's published in Science Advances for a fully 2D structure. And now we are going, they usually see ballistic transport, and now we are going to build fractals with that. So how is the setup? Look at it here to the right. This, you have a lattice. Each of these going along this dimension, this is a waveguide array. And if you look at a cross-section of it, there will be voids in the middle of these arrays. Here you can see the cross-section in the middle, this photonic lattice device. Each of these white circles is a waveguide, and this white line is in between. It has nothing, it's not real. It's just something that we have been putting by hand to show you that when I inject a photon on top here, these photons will hop across these white lines, okay? and suddenly there are voids in the material. The first tiny void up there, it will not be seen because it's just hopping by overlap of wave functions. So the tiny void there in the Sierpinski triangle cannot be perceived, but the other bigger one can be perceived. So it is actually like a second generation Sierpinski, if you want. Okay, let's now look what we are going to get.
So Christine, I'm sorry to interrupt. We're coming towards the end.
Yes.
Just take your time, but.
Okay, but if you give me maybe 3 more minutes, I can finish, okay?
Sure. Okay,
it's
great.
Not missing much more.
No rush. I think there's not a lot of questions yet, so.
Okay, so we are now looking at the quantum transport, and this is going to be given by a tight binding description where you put a tight binding model in a fractal lattice. So when you do that, we will now look at different kinds of fractals. We will look not only at the Sierpinski gasket, but also at the Sierpinski carpet, which now has a different fractal dimension. This one has dimension 1.89. The other one had dimension 1.58. Then we can see how this dimensionality is playing a role. But we also want to investigate something else. And we can go from the Sierpinski carpet into the dual Sierpinski carpet. And the dual Sierpinski carpet comes by taking, you see, look at this generation 1 here, there is this white little square. If instead of getting this little square, I will put a dot in the center of this square. And the same for each other one. Each little white square, I put a dot, and then I get the dual Sierpinski carpet. What's quite nice in this dual construction is that it has the same fractal Hausdorff dimension as the other one, but the distribution of holes, of voids, is completely different. So this will allow us to understand the importance of the voids in the structure. Okay, so we are going to build then the gasket, the carpet, and the dual carpet, which have different fractal dimensions and also different geometries for the same dimensionality. Okay. So that is what we are going to get. We are now going to do the following. You inject light at the top of your triangle, you inject the photon, and in the perpendicular direction is Z, which is equivalent of time, because you will detect them, you make different lengths in these waveguide arrays to measure, to detect them when they come out at different times, which is different propagation length. And now we can measure the variance, the mean square displacement. So the displacement square times the probability to be at that site as a function of length or time, okay? And usually you would expect them in the beginning, when there is nothing there, they should be ballistic. When you look now, on top I'm showing you experiments, and at the bottom the numerical simulations. You see that in the beginning, this exponent is 2.5. It's not 2, and it's not linear, but 2.5. Ballistic would be 2. I explain to you in a second, this 2.5. And then you see that at this value of length or time, it changes the behavior, and it starts becoming, it goes towards a slope that has the dimensionality 1.58. Okay, the slope here is 158. And then at this time, it saturates. Okay, what does this mean? In the classical case, I would expect that the mean square displacement would go with time to the spectral density divided by the Hausdorff dimension. Spectral dimension divided by the Hausdorff dimension. But here it doesn't. It goes precisely with the Hausdorff dimension because we are in the quantum case. It's another proof that we are in the quantum case. So what is going on? It is very beautiful what's going on. Look here. So in the beginning, it starts just diffusing as if it would be in a normal, completely filled triangle. I will show you in a minute why it's 2.5 and not 2. It's because we are not injecting from the center of the sample, but from the boundaries. And then it has this 2.5 exponent when it suddenly finds this hole in the middle. This is at the point 2.675. That is how the photons are at this point. And then it can't go through because there is a void. It starts going around. So you see that the exponent gets slightly reduced. And at 3.875, it went around and it has seen the boundaries of this void. And now it knows it is a Sierpinski triangle. And it immediately picks up the dimensionality 158. I find this incredible, that the photons walk around and touch the hole. And when they have gone around this hole and they have touched it well, they already know it is a Sierpinski gasket. It has dimensionality 158. And they pick up the 158 slope in the sigma square. And then when it comes at 9.275, it has explored, light has explored because of that, okay? The same features, let me just show you now this 2.5. If you do the simulation in a complete triangle and you start injecting light from the top, you will see that the exponent is 2.5. If you would inject from the center, as long as things don't find the boundaries, it would be exponent 2, which is the expected one for ballistic motion. But because you are starting from the boundaries, and you have to, because you will cut the center, you can start from the center, then you start with 2.5. Now, if you would do this for okay, so here you can see again the picture, how it goes in a full triangle and in the triangle with the holes, and you can see all the features that I mentioned before. I don't need to show this again. You can also calculate something called the Polya number. And the Polya number is connected to the probability. So this is the P11, is the return probability. It's the probability that you return to the site 1 where it was injected at a certain time. And if you return any time to the site where you were injected, this probability will be 1, and then 1 minus 1 gives you 0, and 1 minus 0 gives you 1. So if the Polya number is 1, means at some time, any time, you return back to where you were injected. If it's 0, it means you never return back. And when you calculate in the experiment or in the simulations, the Polya number, you see that at 3.875, that was that magic point where it started seeing the voids, you see a plateau in both. So this magic point, 3.875, is also seen in the Polya number. In the triangle, nothing happens at 3.875. If you now do the Sierpinski carpet, look how nice. Now the initial part for a square is slightly different. It's not 2.5, the slope, but it's 2.4. And then when it meets the first hole, it will again lower the dimensionality. And at 5.95, it's when it has met the first hole. You see, it went around, it knows the shape of the hole. It picks up the Hausdorff dimension 1.89. That's the slope of this curve. And here it doesn't saturate because one would have needed to go to much, much larger systems to be able to see the saturation. But what is now very nice is that so if you look again to the regular square, you will see the same things. You confirm the 2.4, that would be expected before you meet the first hole, and then you will start seeing the fractal. Here I can jump. Again, you can see the features at this 5.95. You see a plateau in the Polya number. It's a characteristic of a quantum transport. And what is interesting now is when we go to the dual Sierpinski carpet. Because for the dual Sierpinski carpet, you will start in the fractal regime from the very beginning. And this is because you are finding a hole from the very first site. You see that there is something missing here. So there is nothing compared to the normal crystal, and you enter in the fractal regime from the very beginning. And you also see the other characteristics like this quantized plateaus in the Polya number and saturation when you have explored the entire fractal. Okay, So with this, I came to the end of my talk. I am sorry for my 3 minutes delay. Let me conclude. I told you how to first experimentally build a Lieb lattice with this kind of nano manipulation on the surface states of metals, and how to control the orbital degrees of freedom in space, in energy, and afterwards to separate S and P bands in the honeycomb geometry. I have shown you how to generate flat P bands in graphene, artificial graphene shapes, and then how to design and build an electronic higher order topological insulator state with zero modes at the corner of a Kagome lattice. After that, we have looked at edge-dependent topology in Kekule lattices, which is a beautiful example of how much the edge matters in crystalline topological insulators for determining the topology. And finally, I came to tell you about fractal dimensions and fractals. And I told you how we have built the first quantum fractal in space and shown that the electronic wave function perceives the fractal dimension. And now we went a step forward by exploring how light behaves in a fractal structure like a Sierpinski gasket carpet or a dual Sierpinski gasket carpet. And we could see that light will understand the geometry of the holes, and it will pick up the Hausdorff dimension in the mean square displacement, which was something very unexpected, at least to me. So there are many things that should be still done. We would like to reach the strongly interacting regime. It's not possible with the CO on copper. We need different substrates. We could engineer this on the surface of 3D TIs, get substrates which are heavy that have strong spin orbit coupling. We would like to engineer correlated phases in P flat bands. What else is going to get new there? Understand better topology in fractals. This is very interesting. And to use fractional calculus to connect to these fractals. This is something we have been doing. I will just glance at our recent ArXiv paper, where we have been developing the notions of fractional calculus to study a time glass. So these are all work for future, but let me just conclude by telling you that there is plenty of room at the bottom, but even more in a fractal. And with that, I would like to thank you very much for your attention.
Okay, thank you very much. So we now have a few moments for questions. And if there is anybody in the audience who has a question or a comment, please write it in the chat window and I will see it and we'll proceed. So I see a question from Ying Zhang. Besides working on 2DEG provided by copper surface states, is it worth working on a superconducting surface?
Yeah, very interesting question. It would be. The question is how to pattern. You see, from a purely experimental perspective, why CO works so well on copper? Because when you put these COs at a certain position, you want that the chemistry is such that they stick where they are a bit, such that they don't move, not too much that you can still move them to put them where you want, because some kind of adsorbates, they will just completely randomly self-order by themselves and not form the lattice that you want, but the lattice that they want. So I would say the challenge here is to find which material to put on top of which superconductor, but imagine patterning superconductors with heavy atoms, for instance. It would be fantastic, right? And you need to have something which could be also a surface state, because you want to probe the surface. It is a 2D and not the bulk. So I was thinking of surface of topological insulators, surface states that you have at the top. but maybe on superconducting films, for instance. There could be a possibility.
Well, but didn't Ali Yazdani do things to try to get Majorana states by basically patterning surface Majorana states by patterning superconductors?
Yes,
with
he
magnetic
did. He
rings?
did. Yes, he did some things there. Yes, absolutely, he did.
Mm-hmm.
Yeah, that was bismuth, right?
I don't remember the material. I'm
I
embarrassed
think it was
to say.
bismuth. Yes, he did. That's right.
Okay, so other questions? Perhaps, so here's a question from Xin Lu. What kind of strongly correlated phases would you expect on the system here? And if I could, if Xin, you will allow me to interpret your question a little more broadly, can I generalize that to, you seem to indicate that there were, let's say, some practical obstacles to realizing strongly correlated phases on these surfaces that you've discussed. So can you perhaps also say what in your mind are the key obstacles and what might be done to overcome them?
Yeah, so the main thing would be to find a way to gate our 2DAG, because we would like to tune the density. If we would be able to tune the density, we could go, because we can go into flat bands. If we could tune the density, we could then probably overcome the screening and be able to observe some correlations. The problem is, until now, everything what we measured, we could very well explain with a system of parabolic non-interacting electrons with a renormalized mass, an effective mass. So there does not seem to be any interactions here. But to find, again, it's mostly, I would say, an experimental challenge. I have to say that we are currently investigating something which is more like a way to go behind the corner with that. You can have strongly interacting systems in 1D, which can be mapped into no interacting systems in 2D in well-defined ways. And these we are currently engineering. So we are currently doing the experiments for that. And you can see Feshbach resonances and so on. But again, it's a truly 1D interacting system mapped via a 2D non-interacting one. Right,
I see. So Xin, did that answer your question, or did you want to ask another question? Okay, so the question is, how would you detect experimentally the strongly correlated phases that you get on your surfaces?
Yeah, so we would then need to probe the system, try to explain it without interactions and see that it doesn't work. And then, your system might be strongly correlated, and then you have to include interactions of different types and try to make a model that would explain the measurements. And we know what kind of correlated phases come, right? If you have flat bands, you could get Wigner crystals, you could get superconductivity, Mott insulator, and so on. So by looking at the measurements, we would get a hint whether the states are correlated or not.
Great. So other questions? Perhaps I will ask one while the audience is thinking, and then, I'm sorry, Xin. I'm sorry, just the continuing this line of discussion. Is transport measurements accessible in these systems? I mean, obviously you need cobalt on copper, no, because the copper will short circuit everything. Yeah. But are there systems where you can do transport?
Yeah, so in these systems, not. But what one could do, one could, for instance, convert everything what I have said to, for instance, a semiconductor and put holes by the way how we are patterning, and to measure transport then. That would be possible, to bring this knowledge to different kinds of systems. And that is also why we had, if you want to look at the dynamics, STM can only probe local density of states. If you want to probe dynamics, you need a different setup. And that's why we went into the Chinese collaboration with the waveguide arrays to look at quantum transport and diffusion in the fractal. We couldn't have done it with STM.
Right. Great, thank you.
We could probe maybe correlation. So we could get some more hint about the states by probing correlation functions.
Yeah.
But for this, you need very special setups that can probe different positions at the same time.
Mm-hmm.
And we don't have it. Very few people have that.
Right. Yeah. Great. So if I could ask a question, going back to the Lieb lattice and its cousins.
Yes.
How does your work connect to the various materials that Leslie Shope has been studying at Princeton, which have a somewhat similar flavor, right? She's a chemist and she's been designing materials that are square nets and with different sort of atomic nets with basically 2 in-plane p-orbitals.
Oh, I don't know.
Okay.
So
right. Well,
can you tell me more about the work? I don't know about this work.
It's not my work, but if this maybe would be of interest to the entire audience, I'll at least write her name in the chat. She's in Princeton chemistry, I believe, but is really spiritually in many ways a physicist. Here I'm insulting all the chemists. And, she's on the Princeton chemistry faculty. The name is Schoop.
Okay.
And I'll just put that in the chat so that you can then look up her.
I will take a look. Yeah. Oh, very interesting. So she's building with molecules, she's building
No, I mean, it's really, she's identifying solids that are highly layered and that have this feature of square and possibly other networks which host, you know, pairs of in-plane degenerate or quasi-degenerate p-orbitals and have Dirac points in interesting places. She has been collaborating with Jennifer Cano, who was joint between Flatiron and Stony Brook on this partly.
I see. Oh, I will look. That's very interesting. Thank you very much.
Well, for some reason, I can't make the chat work. So let's see. Oh, that's better.
You have to write it down there in the chat.
Yes.
When you look at the chat, you have to write at the bottom.
Yeah, something went wrong with my keyboard, that's all. So when I was writing, nothing was happening.
Can you say again her name?
Yes, Schoop, Leslie Shope, Princeton Chemistry.
Shope. Oh, okay. Leslie. I know the name.
Yeah.
Okay. Okay. Very good. Okay. Any more questions?
Leslie Shope is a faculty member in the Princeton Chemistry Department. She is, I believe, primarily an experimentalist. That is, her activity is really understanding which systems can be made and making them. And she has been collaborating with various people, including Jen Cano, who's a theorist here at CCQ. So this is now, those names are in the chat. And I'm sure a little bit of Googling will bring you to their work.
Okay, very good.
Right.
Thanks a lot.
So further questions?
There was one, Andy, Adil Amin.
Oh, Adil, yes, I see, yes. Right. So the question is, I'm sorry, somehow I thought that was still from Shin. So is your hope that, the question is, so is your hope, this is from Adil, so is your hope that with flat bands, and if you can increase correlation, you get a plethora of correlated states analogous to what has been proposed for twisted bilayer graphene? And for example, can you get interested correlated states if you make honeycomb lattices or other things?
Exactly, yes. So flat bands, as we have seen with the twisted bilayer graphene, they are extremely interesting because kinetic energy is quenched, correlations become very important, and you can get things like multi-insulating phases or superconducting phases. And now the interesting thing here is that our flat band is a p band. So you get further degrees of freedom, which you don't have in the flat band in graphene.
Right.
In the flat band in graphene, the degree of freedom you have to play is just spin up and spin down, right? Here you get px, py, and spin up and spin down. So you can get a rich variety of phases involving all these internal degrees of freedom in terms of multi-insulators and superconductivity. So it would be much richer than what could be ever reached in graphene because of the orbital degrees of freedom.
Great. All right. So further questions? All right. Well, look, it's getting quite late in Europe. So if there are no further questions, I suggest that we virtually thank Cristiane again for a really stimulating and interesting talk. And we'll see you all next week.
Okay. Thank you very much. Bye-bye.
Thank you. Thank you. Bye-bye.
Bye-bye.
So I'm going to end the session now.
Okay.